Hello, my name is Christian Lopez, and this is my lab report for Lab 1, detailing constant velocity. Introduction. As an intro to this lab, the lab was designed to test the validity of Newton's second law of motion. The law was tested through a lab experiment in which a ball was rolled over a distance. This distance was 8 feet, which was measured by a tape measure, and then its position versus time was observed. This position versus time, these numbers was then used to describe the ball's velocity and the direction that it traveled, further explain or further giving proof to Newton's second law of motion. The purpose of this lab is to observe the motion of an object that is rolled at a constant speed over a set distance without changing direction. Like I said, these results were then to be compared to a computational model. This computational model was designed using GlowScript, a coding software in which you plug in Python code and then it gives you a computational model of the movement of whatever you plug in. And then using this code was done to verify Newton's second law of motion. Some fundamental ideas revolve around Newton's second law of motion. Like I said, Newton's second law of motion is that the acceleration of an object is directly proportional to the net force acting on it, and it is inversely proportional to its mass. This law can be described using a kinematics equation, such as how to dictate its final speed using its initial speed and acceleration and the time interval. Acceleration can also be described as its net force over its mass. If you calculate that, you can get the acceleration of the object. So that's how you can get the first equation. And then the second equation is detailing momentum, that if you have the net force of the object and you have the time interval, you can also find out its delta P, or its change in position. And you can further derive this equation to find out its final position or initial position if you have one or the other. The methods used to go through this experiment were a tape measure that was laid out to cover 8 feet, like I said, a basketball that was rolled from the start of the tape measure to the end of the 8 feet, and then a video that was taken to record the data of that ball rolling. The data was then implemented into tracker software. This allowed us to accurately represent the findings. And then lastly, a GlowScript code was written to build the computational model of the experiment. In this experiment, the system was the rolling ball, and then the surroundings was everything that was not the ball, such as the atmosphere, the floor, the tape measure, etc. So some results, as you can see, my predicted position, that was the position that was used from the computational model, and as you can see, it's a straight line, almost perfect. At time 0 seconds, of course, the position was still at 0, it didn't move at all. And then it seems that as the time increased by half a second over interval, so did the predicted position increase or move at a constant rate of about 0.6 meters per second. This then became the velocity of 0.0 meters per second. And then the observed position, at time 0, it was at 0 meters, and then at the start of the time, the half interval was at 0.75 meters, and then it continued to move at a constant velo of 0.5. So both graphs seem to prove Newton's second law of motion. And while although that, as you can see, the observed position graph does have like a change in slope that can just be described to human error, such as like misinterpreting where the ball was in the video, etc. But the main goal is that for the most part, the slope stayed the same, which proves that if you roll the ball at a constant velocity and have a 0 net force, the ball is going to continue to move at the same speed over that interval. So this is the code that was used to build the computational model, also known as the predicted position. As you can see, towards the bottom of the screen on your left side, lines 35, 36, that's how I was able to get the position and velo. I got the position because, of course, the ball started at a vector of 0, 0, 0, or a point of 0, 0, 0, and then the velocity using tracker, I was able to see that the ball moves at 1.4 meters per second approximately, and then I plugged that into the code, and then it gave me my computational model. And then for the while loop, to show how the ball is continuously moving, you just compare the ball to the position and then you multiply by delta t. Conclusion: the results show that both the computational model and predictive model follow Newton's second law of motion. When the object was pushed, it had acceleration and speed. This speed stayed the same throughout the duration of the experiment because the net forces acting on the ball remained zero or close to zero, thus proving the proportional relationship of Newton's second law. And lastly, what if? If the x-axis were flipped, the data would stay the same, however your graph would now have a negative slope because it would be moving in the opposite direction. And then what does this mean? Is it possible to measure how many forces were acting on the ball? It is not possible to measure the force acting on the ball because since the lab was conducted in an uncontrolled environment, it's almost impossible to measure everything acting on the ball, such as friction, how hard you push the ball, air resistance, etc. Thank you.